And so welcome everyone to our Routing Switching Essentials instructor class for the Chapter 3 discussion, and we may roll in a little bit into Chapter 4 depending on how much time we have here. Getting a little bit of a late start today, but we'll get going. Let's talk about our dynamic routing. Chapter 2 covered everything static, so going in and statically saying that in order to get to this network, go to this next hop or go out this interface. And we talked about both static IPv4 and IPv6 routing. You will notice that this new chapter here discusses RIP version 1 and RIP version 2. In fact, Routing Switching Essentials version 6 now primarily uses RIP as the routing protocol for its examples, which is kind of interesting, but it is there, so we're going to talk about that. And we're going to look at how we route using dynamic routing protocols. Now, we talked a little bit last session about why use static versus dynamic. And we talked about static uses less resources on your routers. Static is more secure because you're saying exactly where the information needs to go. However, static does cause more administrative overhead. And unless you're using floating static routes, typically, you don't have any type of backup if a static route goes down. And we did talk about floating static routes, so that is something interesting. But routing protocols have been around a long time. We can see all the way back to EGP, excuse me, and then IGRP, and it's even before that. You've got all the way down to EGP, going all the way up to RIP version 1, OSPF version 1, and so on and so forth until we've got EIGRP for IPv6, and we got OSPF for IPv6, and we even got BGP with multi-protocol extensions, so BGP version 4. For routing protocols, the big thing that we need to talk about is kind of the different ways that we classify routing protocols. Now, there's two different ways. First, I want to talk about a concept called an autonomous system. So, an autonomous system is a group of routers under the control of a single administration that typically runs the same interior gateway routing protocol. Now, autonomous systems are, there can be, and I think we talked about it this last class too, but there can be autonomous systems that are defined, actually, with an autonomous system number that is a public autonomous system number, and there are autonomous systems that are not defined with public autonomous system numbers. But interior gateway protocols run within autonomous systems. So a group of routers under the control of a single administrator, typically running a single interior gateway protocol. Those interior gateway protocols come in two different, what I call flavors, or two different types, and they're distance vector and link state. We're going to talk about the difference between those in this chapter. But in general, a distance vector routing protocol uses a less complicated metric. It uses a what we call routing by rumor. It's a little more susceptible to routing routing loops because it doesn't have a full, complete understanding of the network topology. Now, having said that, and then we talk about EIGRP. EIGRP has a little better understanding than most distance vector routing protocols, but that is the traditional way we define the distance vector routing protocols. They do typically, though, as distance vector routing protocols, use less memory and less router resources in terms of CPU usage because they do have simpler metrics. And then we have what are called link state. Now, link state routing protocols are protocols that look at the link state of links, send that information out, flood it out to all different link state routers on the network, and then form a topology table, and then from that topology table build a shortest path first, and with OSPF, shortest path first, and from that build out the best route table. We'll talk more about these in depth, but that's the basics. The distance vector is typically considered to be a little less efficient and not as good as a link state routing protocol. Having said that, EIGRP used to be defined as what we call a hybrid protocol. They don't call that anymore. They call it an advanced distance vector routing protocol. So it's a routing protocol that, although it's still performs and has the back-end features are still using distance vector features. It is drawing or borrowing some concepts from link state routing protocols, such as triggered updates and not flooding out the route table every X amount of seconds. And in OSPF or link state, they're considered to be more advanced. So, dynamic protocols. Well, you dynamically share your updates. In other words, you can go out and say, hey, I know how to get to these networks. If a network goes down, you can dynamically send that information out, send out up-to-date information. You can add networks easily and quickly, and those networks will be added into the routing tables. So it's an easier way to manage larger networks when you're doing routing instead of trying to figure out static routes for those networks. Now again, static route uses, most of the time, what do we talk about was the best use of the static route?
Probably a small network.
Small network, definitely a small network with a small amount of network or small amount of paths. What we call stub network. So you see how R1 here only has one way out. So it's a stub network, and that works very well. Really, only very simple stub networks or very simple networks are really where we'll use static routing for all of our routing. Now, we may have a static default route that goes to the internet, and then we inject that back into or redistribute that into our routing protocol. But most networks, modern networks today, are going to use some type of dynamic routing protocol. So there still are advantages for static and dynamic. Obviously, we talked a little bit about this. Static, less overhead, easier to implement, more secure, but not able to recover from network changes and more administrative tasks. Here we see again, this becomes pretty hard to do with static routes. I'm not saying you couldn't do it, but it becomes extremely hard to do and not something I would want to tackle. So what are some advantages of dynamic routing? Well, it's suitable for all topologies. It can work with small and large networks. It can adapt, and I think this is the biggest advantage. It can adapt automatically when the topology or links change or go down and reroute traffic. So it's adaptive. Disadvantage, can be more complex to implement, depending on what protocol you're using. Can be less secure, again, depending on what protocol you're using. Route does depend on the current topology, so you really don't know where your traffic is going unless you're not absolutely certain where your traffic's going. In other words, if you have multiple paths, you know where it should be going, but that doesn't mean, depending upon whether or not a link goes down, the traffic's actually going that direction. And it requires additional CPU, RAM, and link bandwidth. And I will say, to a disadvantage is it does require you to have a deeper understanding of the routing process and of routing protocols in order to make sure you have configured your network correctly. So how do we put router RIP on a network? So here's a simple network, 3 routers, and we want to enable RIP. Well, it's pretty simple. You got our IP addresses on all our different interfaces. We can go into global config and type router RIP, and now we're in router configuration mode. And then typically the next item is just to put in your what version of RIP you're going to use. Now, I talked a little bit, and I should have mentioned this, and I apologize for not doing it, so I'm going to go back just a little bit here. We're going to look, got to slow down, okay? There's one other distinction we need to talk about with the routing protocols. One is, obviously, are they interior, exterior gateway protocols? And then inside of each one of these, there's different types, so distance vector versus link state. There's also an item called classful versus classless, okay? So now, a classful routing protocol, okay, does not support VLSM or virulent subnet masking. Classful routing protocols cannot carry subnet mask information, or do not, in the route table updates. So in other words, they do not support VLSM. they will not work with VLSN. RIP v1 and IGRP, which is no longer even the iOS, are the two classful routing protocols we talk the most about. Classless routing protocols. What do you think they do? Well, they do support VLSN, and they carry subnet mask information in the route table updates. So, RIP v2, all flavors of OSPF, all flavors of EIGRP, all flavors of ISIS or ISIS, all of them supported. BGP also supports VLSN. So almost every modern routing protocol supports VLSN and carries route table updates. The cool thing is, if you look at the RIP version 1 update information and look at the actual packet creation or packet rules, and then look at RIP v2, the only difference is that RIP v2 allows you to carry subnet mask information, and RIP v1 doesn't. So be aware of that there are classful and classless routing protocols. Very important in our modern networks, we should be running classless routing protocols because we're going to support VLSN. Now, when we get into here and we look at RIP configuration and it talks about doing router RIP, if you just do router RIP and then start putting in your network statements, you're running RIP version 1, which means you do not support VLSN. If you want to run version 2, you do router RIP and then put in command version 2. Okay, and so those are items to be aware of, and they don't really talk too much about this here, but they talk about there's the version, set the protocol version. You're going to play with both in the chapter, but we typically would always want to run version 2. We typically, honestly, would never run RIP to begin with, but that is what it is. We can use it to study routing protocols, and it doesn't hurt anything. So router RIP, and then notice you advertise only your directly connected networks. I see this all the time. I see people trying to advertise all the networks in the network on, say, R1. Well, that's not going to work because the routing protocols that we deal with in CCNA, they will only advertise networks to which they can actually be, well, they actually have a connection. So in other words, R1 has a connected network to the connected interface on the 1.0 network right here, and on the 2.0 network right there. And so it will advertise those networks. And you need to advertise those networks. So you need to put those in. So on R2, how many networks would you advertise on R2?
Looks like 3.
3. Yep. Based on talking about it would be 3. So you'd want to do 2.0, 4.0, and 3.0. And in R3, you would also advertise 2 networks, 4.0 and 5.0. So that's what they do here with this little, they have you do a quick little Quizlet or Simlet, and you put those in, and you go in and put in the networks for those. Now, again, this is going to be running RIP version 1 because you didn't change the version number. If you want to verify RIP, you can do a show IP protocols, and you will see that the routing protocol is RIP. You also see that you are default version, send version 1, receive any version. So you're actually sending version 1, and you will receive 2. But as long as you're running sending version 1, you're going to be class full. You also see automatic network summarization is in effect. This means it will summarize to the major network boundaries, the classful boundaries of class A, B, C for the routing protocol updates. Shows you the networks you're routing for, and then it also shows you items that we'll talk about, sending updates every 30 seconds. Now that is a key thing about RIP. RIP does send its entire route table to every directly connected neighbor every 30 seconds. Now, technically by RSE, RIP is not supposed to send triggered updates. Now I will tell you that the Cisco version does send updates when you make a change. It will go ahead and automatically send out the route table. But here's something that's interesting about RIP. Think about the waste of bandwidth that you have when every 30 seconds you send your entire route table out to directly connected neighbors, even if there's no change. Now, there's also a problem with that. If you didn't have the updates, the immediate updates that the Cisco iOS RIP version will send out, think about a change that took place 1 second after you sent your update out. With traditional RIP, if you didn't send another update out till you went and reached the timer of 30 seconds, it would be 29 seconds that your neighbors would have incorrect information in their route table. So it's not a great protocol in that respect. Now, they've done some things to kind of make it better, but it's still, honestly, not a protocol we're going to run in the real world. But it's got concepts in it that we need to know. Concepts such as timers, how often are invalid after 180. That means after 180 seconds, items in the route table will be marked as not valid if it has not been updated from a neighbor. Hold down will be how long it holds it in there before it flushes it, and then it flushes it after 240 seconds. Now, here's the neat thing about routing protocols. They do all this for you automatically. You don't have to worry about making a change once you've set up your routing protocol to handle the networks that are on it. Here's one thing I'll tell you about RIP. If you've ever played the game where you start, you tell someone in a room a statement, and then you have them whisper it to everyone and go all the way around, by the time it gets to the last person in the room, it has no resemblance whatsoever to what you actually told the first person. This is the same for RIP. Remember, this is routing by rumor. RIP only shares its routing table updates with its directly connected neighbors, not with anyone else. So it can be a problem. Now, how do you enable RIP version 2? Well, you do router RIP. You type in version 2, and now you're running RIP version 2. You'll be sending and receiving version 2. So be aware that if you do a no version while you're running version 2, that will take you back to version 1, which is the default sending version 1 and listening for version 1 and 2. If you're going to change 1 to version 2, send all to version 2, because version 2 supports VLSM, version 1 does not. Okay. So again, no problem here. It's just type version 2. Now, auto summarization, even with RIP version 2, auto summarization is in effect by default. So if you do not put in this command, no auto summary, even though RIP version 2 supports VLSM, your router will do automatic summarization, which could be a big problem depending on how your network's been designed and set up. So this no auto summary command you need to include in almost all of your RIP configurations, because you're going to set it to version 2 and you're going to do no auto summary. Otherwise, let's imagine if we had a little different network here. Let's imagine, I'm just going to drag this over here and do it like this. I need to have my service tablet running on this, but I'm going to imagine, let's imagine R1's Ethernet, okay, was 10.0.1.0/24. Okay, oops. It helps if I can type. And let's imagine that over here, all the way over on R3, let's imagine R3's Ethernet was 10.0.2.0/24. Okay, and let's say we're all running RIP version 2, so RIP v2, but we forgot to turn on no auto summary. If we did that, RIP R1 would advertise, it would say, hey, you know what? It would tell R2 that it knows how to get to the 10.0.0.0/8 network. And likewise, R3 would advertise that it knows how to get to the 10.0.0/8 network, because they would auto summarize this to the major network boundary, because you've got a different network in here. You've got 192 networks in between here. And then R2 would have 2 equal cost paths, because remember, RIP uses what's called hop count. That's just the number of routers it goes through as its metric. So RIP R2 would think that the 10 network was available 1 hop away on R3 and 1 hop away on R1. As soon as you turn on the auto summary, however, then R1 actually advertises 10.0.1.0 and R3 advertises 10.0.2.0, and that would fix the problem. So be aware of that. That's what we mean by automatic summarization, that it will summarize, especially if there's a boundary between, like 192.168 and these 10 networks that would imagine they were on the Ethernets over here. So, any questions on that? Some other items that are interesting about RIP that can be a problem here is this Ethernet interface right here is connected only to a switch and to no other routing device. But I told you that R1, or actually all these routers, will send their entire route table out every connected interface every 30 seconds. Well, it's broadcast out, depending on which version you're using, B1 or B2. But it's sent out this interface. Well, that's wasted resources because you don't need to send it out because there are no routers over here. You can configure what is called a passive interface. So you can go to R1, passive interface gig 00, and that interface will listen for any incoming RIP updates, but it will not send any out. Now, you would never want to do that on an interface that's connected to another routing peer. So you want to do it on the network between R1 and R2. But really on R1, you should set G00 to passive and do the same for all the other Ethernets on these routers, as long as you know for sure that you will never put a routing device out there on that interface. You also have the ability to do what's called passive interface default, which would set all interfaces on the router to default, and then you do no passive interface on an individual interface. So,
is that assuming that the switches are layer 2 switches and not
correct.
Layer 3? Okay.
Correct. Yes, that would be assuming, again, as long as the switches are not doing any kind of routing, there's no routing at all going on out there. Now, if you were doing routing on it, then you would need to leave it on if you were running RIP. So exactly, yeah. If those switches had to be layer 2 switches. Now, how do we propagate a default route? Now, what does it mean by propagating? It's sometimes you hear it injecting a default route into your routing protocol. Sometimes you'll hear it, you redistribute static, depending on if it's the IGRP. But basically what we want to do is we've got this network here, and R1's connected to the internet. So we've done a default route on R1 going to the internet. Instead of having to go to R2 and put a default route going to R1 and R3 with a default route going to R3, we're running a dynamic routing protocol, so we don't have to do that. So we don't have to go to all these other routers and put in static routes. So what we can do, and I used to call this the magic dust command, but in RIP, we can actually go into R1 under router RIP and do default information originate. This will then propagate this static route to the other connected neighbors that are running RIP. Well, not disconnected. It actually propagated it to R2, and then R2 will then propagate it to R3. So you see here, R1 has the static route, quad 0 going out S0 is its fully qualified static route, by the way. It's quad 0, outgoing interface, next hop. Under RIP, you got default information originate, and you'll see there's a static route that's available. Okay. And then if you look at R2, you would see, once you did that on R1, you would see a RIP route, RIP R star, which means candidate default. You see a quad 0 route that's available via 2.1. So in other words, R2 has learned its default route via RIP. And now it knows anything it doesn't know how to get to, R2 will send that over to R1, and R1 can use that static default route to send it to the internet. Okay. Same thing with R3. If you look at R3, it's got a candidate default route that says go over to R2, which is 4.2. And all of that was accomplished by setting up the static default route out and then putting default information originate in RIP. Now it works for version 1 or version 2. And it will inject that static default route or propagate that default route into RIP. And it's propagated all the way through. Now, here's one of the things to remember. RIP has a 15 hop count limit. So on the 16th hop, it will be marked as time to live will be marked as unavailable or exceeded. And so RIP is only useful in small networks. If you had more than 15 hops, it won't work. We have a basic lab on configuring RIP v2. And again, remember I said that we're working on, this is configuring RIP v2 and RIP ng. So you see the lab here, the content. Okay. And if we look inside the right here, the lab, the difference is it's just RIP v2. So they basically took out the RIP NG that was part of the lab before. So I'm pretty sure it still works exactly the same because there's no real difference other than the IPv6 addresses that you've got down the road. So be aware of that when I send out the labs, that you can do the same lab on NetLabs. It's just got a slightly different setup. They removed NG. That's it. It actually makes it a little bit easier, I think. So, okay. So route table entries. What's in the route table? When you look at a route table, you will see the way the route was learned, okay, the network the route is associated with, how it is connected to the router, okay, and then other items. So for instance, in this one of RIP, this is the network 209.165.200.228/30. 120/1, this is the administrative distance, so that is the trustworthiness of this route. That's the number of hops, that's the hop count. That's where it was learned from, okay, how long it's been in the route table, and then the interface that is connected to it. Now, the structure of the routing table is defined, even though it's classful, it does have classes and classful. The structure is still built around the classful scheme, so you will see parent routes and child routes, and we'll talk a little bit about those more later as we move along. But look here, directly connected routes. That is some routes that are connected to the physical interfaces on the router. We notice there are L routes or local routes, which are new to the 15 iOS or higher. And that's the actual IP address on the interface. Okay. The route source, how it was learned, destination network, again, outgoing interface, those are all there. That is a static route. D is EIGRP, and by the way, do a show IP route, there's a table that tells you all this. O is OSPF and R is RIP, but you probably need to learn those too. So, but here we can see directly connected, the network, and the identifier. Remote network entries, there's our source, destination network, administrative distance, metric, next hop, timestamp, and outgoing interface. So remember, AD is that trustworthiness. That is really defined by Cisco. You know, RIP is 120, EIGRP is 90, OSPF is 110. Lower is better, so the lower AD is considered better. The metric is how the route protocol determines the best route to put in the route table. Each one of the routing protocols has its own metric. RIP uses hop count. Each hop is a single item in the metric. Least number of hops is considered best for RIP. Other routing protocols use other things such as cost with EIGRP, or excuse me, with OSPF, or the metric for EIGRP, which is bandwidth plus the sum of the delays. Now, when we look at the routing table, there are some terms in the routing table that we need to talk about because it's not a flat database, it is hierarchical. And we're going to look at some things such as ultimate routes, level 1 routes, level 1 parent route, and level 2 child routes. So first off, let's talk about an ultimate route. That is a route in the route table that contains either a next hop IP address or an exit interface. Okay, so directly connected routes, dynamically learned routes, and local routes are all ultimate routes if they have those items, and that is a next hop IP address or an exit interface. Okay, so notice here, these are all ultimate routes because they have an outgoing interface or next hop IP address. And here's the next hop. You can see here via this, via this, via this. Those are all ultimate routes. A level 1 route is a route with a subnet mask equal to or less than the classful mask. Okay, equal to or less. So it can be This, you notice, this is a Class C address, and this has the equal to. Now, this happens to be a level 1 ultimate route because it does have a next hop IP address or exit interface. There can be level 1 supernet routes because it's less than the classful mask. And the default route is an ultimate route. That's just by default, it's considered a level 1 route, and it's also an ultimate route. So a level 1 route has a mask equal to or less than the classful mask. So here we can see that this is a level 1 route, level 1 ultimate route too, because it's a default route. And then here's one, this is a RIP route that is less than the classful mask. And so this is a level 1 ultimate route, because it does have a next hop, and it also has an outgoing interface. Okay. Now, there are level 1 parent routes. Now, what does that mean? That means it is a route that has been subnetted and that has child routes under it. So when we look in the route table, we will see that level 1 routes that are parent routes do not have next hop IP addresses, and that so they therefore level 1 parent routes can never be ultimate routes. We see here now, and this route table is a little messed up because of the way that the route table is shown, but you should see this is the parent route, 209.165.200.24, Beverly subnetted, 5 subnets, 2 masks. You'll notice that down here are all of the child routes. All the 209 routes, these are level 2 child routes, and you'll notice those are also ultimate routes because they have next hop. The reason this is important is because it used to be, when we did classful routing, it used to be that if you went in here and fell down into the parent route entry and you looked all through the child routes, and there was, let's say there was an IP address or an IP that was some part of 209.165.200 but not represented by these child routes. It used to be that if you were class full, it would fall down into here, and then if it didn't find any route in the child routes, that particular packet will be thrown to the bit bucket. Even if you had a default route defined up here, it would not matter, because if you're doing classful routing, it wouldn't care, it would chuck it in the bit bucket. Today, with classless routing, what will happen is, even if it goes into these child routes, if there's no matching child route for the destination, it will come back out and go into the default route. Okay. So what happens here is a level 1 parent route is just basically a heading for subnets. That's what it does. And then level 2 child routes are those routes that are in fact child routes under a parent route that are also ultimate routes. So here we have the parent route, and then we have child routes. So here's our parent route, here's the child route, and they're typically, well, they're not just typically, they're always going to be ultimate routes. So really the hierarchy here, as you can see, here is another parent route, 172.16.00/16 Beverly subnetted. Here's all the child routes, and all these level 2 child routes you can see are ultimate routes because they do have an outgoing interface or next hop IP address. So we have ultimate routes. We have parent routes, which are level 1 routes, level 1 routes that are either equal to or less than the classful mask, and they can be ultimate routes, typically are ultimate routes. And then, go ahead, Kurt.
Well, is it preferable to have both items in there, the outgoing route and this IP address or next hop? Or does it really matter?
It depends on the routing protocols are going to put that in automatically for you. Now you're talking about for the static route, it's typically preferable over multi-access networks to have both, have fully qualified.
Okay.
But your routing protocols are going to put in both automatically for you. They're going to put in your next hop IP and the outgoing interface, unless it's just a connected interface. Then it goes in the route table as the outgoing interface. So when you look here, you'll notice that this was a static route put in as a fully qualified, what I could call fully qualified, because it's got next hop and outgoing. These all have it because RIP automatically puts that into the route table. Does that make sense?
Yep.
So not only is it confirmable, it happens automatically, so it's not something you can really control. But let's remember, an ultimate route has a next hop IP address or outgoing interface. Level 1 route has the mask equal to the classical mask or less, and they are ultimate routes. Okay. Level 1 routes are also ultimate routes. Level 1 parent routes, okay, are routes that have child routes under them, and they're really just a placeholder, a heading for subnets that will come under them as child routes. Level 1 parent routes are not ultimate routes. Level 2 child routes are those subnet entries that you've learned, and they are in fact ultimate routes. So, and also a good thing here to notice, even if you're running classless routing, parent route is going to use the classical mask. So you see this 172.16.0.0/16. That's in there for the parent route because this is the classical mask for this IP address. Then underneath that, you see our variable length subnet mask item. Okay? And really this discussion just helps you to see how the routes are put into the route table and how we look at this route lookup process. So basically, here's what happens. First thing you're going to look for is a level 1 route that matches. All right. If the level 1 route matches and has the longest bit match, then it is going to proceed to the next step, which is to send it out. So if the best match is a level 1 ultimate route, then that route is used and it goes out the interface. If it's a level 1 parent route, it has to change a little bit. It actually has to go in and look at the child routes. So to go down and look in the child routes to see if there's a subnet that can be used to forward that packet. If there's not one, it will then actually come back out and look for supernets. And if there's no supernets, then it will look for a default route. Now, what a supernet is a collection of networks bound together. It's a summarization of networks. So like this supernet of 192.168.0.0/16 is all those networks together. So it's basically 0 to 255 in the network. You'll notice too, if this network route and the supernet route were in there and something was destined for 1.10, it would use the longest bit match. So this matches 2, okay, but this is a longer bit match, so this level 1 ultimate route would be used to send it out. Now, here's one thing that's important too. If you go back out, you go down through the, you look at the parent route, you go down into the child routes, there's no match, you go up, there's no supernet match. If there's a default route, we use the default route to send it. If there's no default route, in other words, if a router looks through its entire route table and finds no destination route or no route for the destination network, that information in that packet will be automatically put in the bit bucket. It'll be dropped. Okay. Now, one of the things you got to understand here is with Ceph, again, remember that goes and looks at the entire route table and builds a preset lookup table that's already built that you don't have to actually go through and do lookups for. Without Ceph, it would have to go back out and do a lookup if you were doing, if there wasn't an exit interface for the next hop for the route. But because of the way that Ceph works, now basically it has all that information in the Ceph table. So once you find a route that matches, boom, it goes out immediately. Actually, we'll just look in the Ceph table and do it for you. Do remember again, the best match is the longest match. So there's multiple routes. Okay. So let's say the destination is this 172.16.0.10. All right. And this is what it's looking for, the longest match. If you look through all these matches, the route that matches the most number of bits will be the one that's used as the one to be sent out. Okay. So /12, which only matches the first 12 bits, well, those match, but wait a minute, the first 18, those match too. Now we go to /26, and once all 26 of those bits match, that means this route, the third route, will be used to forward this particular packet. One of the key rules is longest match wins. Now, how does IPv6 work? Well, to be honest with you, exactly the same. You got an IPv6 route table. Okay. You got route sources. You got directly connected. You got your administrative distances. Same thing if you're running a routing protocol. Okay. In this case, we're running EIGRP, so it's 90. No real difference here. You still have same concepts. Network entries for remotes, the same thing. You look at it, you've got, the source, remote network, destination network. You got administrative distance, your metric, the next hop, which in this is a link local next hop, okay, and then the outgoing interface. So very, very similar already to what we've done. And then, folks, that's it. That's chapter 3 in a nutshell. Much simpler even than it used to be, quite honestly, for that chapter. Any questions? All right, I'm going to stop the recording.